Hello fellow students, this is a recreation of the Beambot video that Professor Smith submitted on Moodle. In task 1 you will see that I have S1, S2 and L1 and L2, where S1 and S2 normally would be your sensors, but in this case you can just represent them as a switch with some wires. L1 and L2 are your LEDs that you can clearly see from the diagram. Currently, I have labeled the S2 to be orange and S1 to be blue. You will see that I connected VCC to pin 14 and VCC to the two 10K resistors. VCC is 5 volts. I've also connected pin 13 and 12, 11 and 10, 1 and 2, and 3 and 4 together. You will see why in a moment. And then my pin 6 and pin 8 is my output pins. In this particular case, you will see that, for example, if we make S2 low and S1 high, I will get that my output L1 for LED 1 is high and my L2 is low. And the process is as following. When you look closer to the diagram, you'll see that for the S2, when it is 0, it goes down here to to pin 1 and pin 2, where both of them will be low, and the output will be inverted to 1 because it is NAND. And that follows over to pin 4, where we made S2, which is the blue wire 1, or high. Now it follows all the way through here to pin 5, and then we get a low output because of that NAND concept. If you look at your NAND truth table, where 1 and a 1 is 0. And so then our output for pin 6 is 0, and our LED will be off. The opposite will happen here at the top, where now S2 is low, which will follow all the way through here to pin 9, and S1 is high, which will be high on pin 13 and 12. They will give a low output there for your pin 11, then pin 10 will be low, and since both 10 and 9 are low, output 8 will be high. And then our LED 1 is then high. And that summarizes the task 1 diagram. So here I have all of the components laid out on a breadboard to visually represent what I just talked about in the diagram. You will see, if you look closely here, I have two 10K resistors coming from my input terminal here at the top. Let me just point it out. This is my positive input terminal where the 5 volts comes in. Here at the bottom terminal, I have grounded everything. Then both my 10K resistors receive 5 volts. My pin 14 of the quad NAND receives 5 volts, as well as, oh no, yeah, that's about it. Then here's the pin 7 that is grounded, and all of the other things are grounded as well. I just have not added the wires yet because I'm going to do it now. You will see here as well that I have connected here pin 13 and 12, pin 11 and 10, pin 1 and 2, and pin 3 and 4. And then here's my pin 6, which is the output to the blue LED, and pin 8 here is the output to this yellow LED to make it easy to follow along. Okay. Next, we can put in our wires. So for example, I will use gray wires for S1 and I'll use green wires for S2. I'll put in the gray wire here at pin 1 and I will connect it here at the bottom just to be somewhere quickly. Then the other gray wire I will connect to pin 5, which is also connected to S1. As you can clearly see, here's the gray wire, here's the other gray wire. Then I will take green wires for S2 and I will connect the one green wire to pin 1. Just let it lay there. Okay. And I will connect another green wire to pin 9. Up here. There we go. So you can clearly see there's the same as the diagram. There's the top part, which has your S1 and S2 and then the bottom part which has S2 and then S1. Now, if I take similarly to the diagram, I have here a purplish wire for S1, and then for S2, I have an orange wire that I can plug in here. Okay, can you see clearly? There's the green connected, same as this junction here. And then here is the S1 connected, same as this junction here. Now if I connect VCC, currently both should be on as they are. The blue LED for pin 6 and the yellow LED for pin 8 is on because both of my input signals are low. So when you put your wire into the breadboard, it views it as a low, and if you take a wire out, it technically goes high. So because I just pulled out S1 and made it high while S2 is low, we should have that my output pin 6 should be low, which it is, and pin 8 is high, just as the diagram showed in the previous explanation. Then if I alternate between them, I should get the opposite reaction when I make S1 low and S2 high. And if both of them are high, both LEDs should also be on, according to the logic. For task 2, we will only replace the wires that we use for switches as the inputs in the previous task with the IR LEDs and the infrared photosensors. So what you'll notice is that the quad NAND and the LEDs for the output all remain the same because the logic should not change, but we just want to replace the inputs. So in this case, you will see that we now have placed the IR LEDs with a 100 ohm resistor connected to VCC and to ground. And you will also see that the only other change is that your S1 or S2 is your photosensor that is connected then to your 10K resistor. You'll also notice that if you look at the way you normally connect an LED, the photosensor has to be connected in reverse. Otherwise, you will not get a result out, in this case with the BeamBot. And if you have your diagram with you, you can see that you must connect your emitter to your VCC and your collector must be connected to ground. That way you will get a current passing through it to either be passed through to ground or through to the quad NAND. In this particular case, the way it works is that whenever your photosensor is receiving infrared light, its resistance is about, let's say, 100 ohm or around there, allowing for current to pass through the circuit, almost like in the previous case with the regular wires. In this case, because if we make it dark, then we will see that the resistance suddenly goes to a mega ohm or very high. And that results that there's blocking off the current to go to ground, and the current will rather flow through to your quad NAND. And so, as you can see, that when it is light, you should get a low output around 0.01 of the VCC. And if it is dark, or if you block for whatever reason the light from coming into the photosensor, you should get a high towards the output. Looking at the breadboard, we can see that there are no significant changes made to the rest of the circuit as discussed in the diagram. Here are still my gray wires and green wires that represent the wires coming from S1 and S2, and my LEDs are still at the same spot. The only difference is now I've got all of my resistors here wired to the top, so you'll see that there's the 100 ohm for the first R LED, then the 10K, then 100 ohm, then 10K. You can also see that I've made blue wires to go to the first LED, then the second sensor, and then the next LED, and then the next sensor. If I turn it on, the logic should remain the same, where both are on when both are receiving light. When I block S1, the output at pin 6 should go off. When I block S2, the output at pin 8 should go off. And if both are blocked, both should come on again. And therefore the logic works. We can also now see how the voltage changes when we wire up an oscilloscope to the sensors. Because of the way this is wired and the photosensor is put in the reverse, when the light is coming through, we should see a low on the oscilloscope, which is what we do see when looking at it. Whenever we block the incoming light, we should see a high. And there you can see clearly that when the light is being blocked, we are receiving a high. The same will be on the other photosensor. If you were to swap the photosensor's emitter and collector, you should get the reverse concept where you have a high when there's light coming in, but a low when the light is being blocked. This might be a bit difficult to see, but I have blocked off the S1 and the blue LED is off, and I'm now measuring the input signal that should be given to pin 5 and pin 14 and 13, and we should get 3 volts going through to the quad NAND. For task 3, we now connect the Darlington transistor, 2 diodes, as well as the 2 motors into our circuit. We will see that the quad NAND and all of the previous stuff with the sensors all remain the same, as that is now wired up correctly for the logic. We now have pin 8, that is the output for our quad NAND, and pin 6 connected to the pin 1 and pin 2 of the Darlington transistor. Our motors are connected to VCC as well as through a diode towards pin 16 and pin 15 of the Darlington transistor. It doesn't matter which way you connect the motors, they will run either way. However, it is recommended to connect one opposite from the other to make sure that both of them will be rotating in opposite directions. Otherwise, your beambot will just spin in a circle when you eventually wire it up. Another thing is to remember is that the common pin 9 is ignored and pin 8 is the ground. These symbols inside the Darlington transistor do not invert your actual signal. You will notice now in the example that I will do that when I wire pin 6 to pin 2, that it does not change the signal from high to a low to allow for the motors to run. The Darlington transistor simply acts as a signal amplifier to allow for control over the motors. Otherwise, if you just wired the quad NAND to the motors, you would not be able to control the motors with the signal. Once again, looking at the diagram, you will now see everything remains the same. We still have our S1, S2 wires. The sensors are wired up. The only difference is now the Darlington transistor is connected. It does not have a VCC. Obviously, here's our ground wire for pin 8. The diode must be connected to, let's say, pin 2 in this case. I only have one motor. And then the motor is connected to VCC through to the diode. And then the input signal comes from the quad NAND. You will see here I've connected it to pin 2 to be able to control it, and it is connected to pin 6. The LED and the motor is now connected to pin 6 of the quad NAND. So when I wire it up, in this case, the LED comes on, the motor is just a bit stuck. You should see, there we go. If I block it, it doesn't want to run. And if I allow for the signal to come through, it runs. You will also see that the motor is in this case drawing about 3 volts from the circuit. If I let it run, we can see there the line goes up. Okay.